Okay, we're going to begin the seminar. Uh, Today's distinguished lecturer is Dr. Evelyn Hu from the University of California at Santa Barbara. Dr. Hu is a well-known expert in materials processing and devices, and she has a very distinguished career that extends back to uh, receiving her PhD at Columbia University. I just found out that it was in particle physics, of all things. So now she's dealing with really tiny particles, well, macroscopic compared to atomic particles, quantum dots. She spent 6 years at Bell Laboratories after uh, getting her PhD, and then came to University of California, Santa Barbara, where she has held a variety of positions that have aided the rapid growth of that department in photonics and in nanostructures. She's currently the director of the California Nanosystems Institute, which is a joint center between UC Santa Barbara and UCLA. And she has previously held positions as director of NSF centers in quantum systems, the so-called QUEST Center. Her research focuses on high-resolution fabrication of compound semiconductor, electronic, and photonic devices. And for her many accomplishments, she's been inducted into the National Academy of Engineering, and she holds fellowship in a number of the major societies, scientific societies, APS, IEEE, and the AAAS. And she holds an honorary doctorate degree from the university, and it didn't print out. What university? Okay. I didn't understand what she said, but I'll just let that slide. You can read it on her bio. Today, her talk is Thinking Inside the Box, Quantum Dots Tuned to Photonic Crystal Cavities. It's a really interesting subject, and we're looking forward to hearing Dr. Hu speak.
Am I on? Thanks very much, Dan. I'm really delighted to be able to speak before you today about something a little bit different, thinking inside the box rather than thinking outside the box. Before I tell you what the box is and how you should think, I'd like to just acknowledge my collaborators on the series of projects that I'm going to talk to you about today. There are actually many, many more people than are listed here, but I wanted to particularly single out my fellow faculty members, Pierre Petrov and Dirk Baumeister at UC Santa Barbara, and Atache Mamoglu at ETH Zurich. But in particular, the names in red, Kevin Hennessy and Antonio Badolato. I'm going to tell you an incredible story of development that and reaching a goal that was very difficult to reach that started when both Kevin and Antonio were graduate students. They're now postdocs, and Kevin goes back and forth between Zurich, and Antonio is a postdoc at Zurich. And so I'm going to tell you a story where we've made an incredible amount of progress because of our collaboration, because of their particular collaboration and insights over the period of a PhD thesis. The remarkable progress is largely to a number of insights and incredible collaboration in an integration of a variety of different techniques. So let me begin with this title, Thinking Inside the Box. Maybe you've heard the caveat, the admonition that people should think outside the box, should go beyond the confines of their usual perception of the world. If you really want to make a leap of innovation, if you really want to do something dramatically different, you should get outside of your comfort zone, get out of your box, and take another look at the world. And so I'm asking you to think inside the box. And the reason is the following. Why would I say stay in your little your box? Well, it depends on what kind of box you're talking about. And sometimes you want to get into that box and take a box eye view of the world to get some insights into how to engineer things differently. And this is the box that we're talking about. We're talking about optical emission. And let's begin with some kind of emitter. So we have a ground state, an excited state. These are electronic states. And we can have an electron promoted from ground state to excited state, and then it can de-excite again. And very often when that happens, when it de-excites, it can emit a photon. And here is another example of an emitter. We make the transition from ground state to excited state, make a de-excitation with the emission of a photon, and go back and forth. And usually, not often, but usually, that's the end of the story. You've done an excitation, you've tickled an emitter, and that emitter can be an atom, or as you're going to see, it's going to be an ensemble of atoms that we call a quantum dot. And you emit that photon out into the world, and that's it. That photon does something. It illuminates, you record it, it reflects off something, but that photon and its characteristic emission lifetime has to do with the nature of the emitter generally. And within boundaries, there's very little that you can do to dramatically change that. And what I'm going to do is to make a shorthand for that emitter. This equals this symbol, and this symbol is going to be an exciton. Some of you already know what an exciton is. It's an excitation with a hole and an electron in a quantum well, in a quantum well or quantum dot. I'll get back to that later. But for the moment, this is a shorthand for the emitter and for the transition of electronic states. Now, when I talk about thinking inside the box, think about a box. Think about changing dramatically the optical properties of that emitter in a way that you can control its lifetime, control when the emission happens, control the efficiency of pumping energy into the environment and getting the energy out. What might that box look like? In this case, the box is something we call a cavity. So I'll represent the box by these parentheses. And what the box, this cavity is it's a cavity in the sense like an organ pipe is a cavity. You all know that an organ pipe has a certain length, has a certain aspect ratio. It's an acoustic resonator, an acoustic cavity. And depending on the geometry of that organ pipe, you blow in and you get a standing wave, you get hopefully a pure tone. You get the response at a certain frequency. Well, this box is an optical resonator, and I've shorthanded the characteristic standing wave or resonant mode, resonant response of that box by this wiggly signal. And another way to think about it is as we had the electronic states here, ground state and excited state, we now have in this cavity allowed photon states. And you can have an unoccupied photon state or an occupied photon state. So that's our emitter. And this is the box. And what is it about that box that might, from the box side point of view, change dramatically the behavior of that emitter? Well, let's rearrange everything on this view graph to look like this. And what we have is the box. We have the resonant modes. And now let's look at the emitter at the box side by side and think about what's happening in terms of excitation, electronic excitation, de-excitation, photon emission. And instead of the photon going out, losing it into the environment, let's capture that photon within that box. And in particular, when we capture the photon, we're talking about perhaps having that photon in a resonant way populate the allowed photon states in our box. So we're going to have to engineer this box very carefully. And when we engineer the box like this, what we want to do is here's the mode, the standing wave, we want to place the emitter at the maximum of the electromagnetic field. So this box has modes. Those modes have energy. There are energy densities that, and it has a spatial profile. And we would like to most strongly influence that emitter by the electromagnetic field in this box by placing the emitter at the maximum of the electromagnetic field. And that's what I'll call spatial resonance. And the other thing we'd like to do is, as shown here, is match the electronic transition energies with the photon energies, and that's spectral resonance. That is, this photon coming out is resonant with a photon state that exists in the box. So I have two kinds of resonance, two kinds of matching, spatial resonance and spectral resonance. And what happens if I have that? I'm going to show you a few examples of what happens when I have that. But among the things that can happen, the creative possibilities of this different box is the control of spontaneous emission lifetimes, ultra-low threshold optical sources because of that matching between electronic states and photon states, the ability to control the environment, and therefore by controlling the environment, control the emitter within that environment. So a possibility of generating controlled single photon sources, that is, controlled emission of photons on strategic triggers that you make to the environment. And in general, although I won't go into great detail about this, but perhaps you will sort of get your own insights as I talk about this, this serves as a very useful quantum information testbed, as you may see. Now, everything that I'm talking about, some of you may have seen this before, and the representation I have of this box or cavity and an emitter within that, it's part of a field called cavity quantum electrodynamics, or QED, cavity QED. There's been a tremendous amount of work of cavity QED done for single atoms, so making a box that is resonant with frequencies of single atoms that exist very rarefied basically in vacuum. But what we're talking about is something different. For those of you who studied semiconductors, you realize that this kind of configuration in the solid state in semiconductors can become very challenging. So the next part of my talk, as part of the introduction, we'll talk about exactly what emitter we use and what box we build to match the properties of that emitter. So I'm going to introduce the critical elements, the emitter and the cavity for this solid state configuration, show you how we put together the system, how we do the fabrication and initial measurement, and then give you some examples of those points, those creative possibilities that we can achieve once we put the system in the right box, which is efficient energy coupling. I'll show you an example of a laser with incredibly low thresholds to lasing. I'll show you, remember I talked about the important points of frequency resonance and spatial resonance. And how do I achieve that? If I make the emitter and I put it in the right box, presumably when I do it first shot, I don't get it exactly right. So how do I fine-tune the emitter and the box so that I do get that spatial resonance and that frequency resonance? So I'm going to talk about that fine-tuning process, how we tune the modes of the box, how we change them in a controllable way, and also how we control the position of the emitters, which in our case are going to be quantum dots, how we control those positions within the box. And then ultimately making the match. If we do everything right, if we match the properties of the emitter to the properties of the box, we get something called strong coupling, and I'll show you what that means in a minute. And strong coupling, actually, these results that were just realized a few months ago, instead of giving us new answers, and these results did give us new answers, also generated new questions. So that's how we're going to proceed. And just then as we proceed, let's take a look again at what we might want from our system. So I'm going to talk to you about the critical elements, but before talking about the critical elements, what do we need of those critical elements? What are the requirements? Well, for the box to influence the emitter And later I'm going to use the word coupled to the emitter. That is a cavity coupled to the quantum dots. What we need is, we need a high concentration, a high energy density electromagnetic field. So what we would like is a high field density within a small spatial volume. So it has the concept of high energy density. It also has the concept of small spatial volume. We want emitters, if you look at the symbol for emitter, with high optical efficiency. That is, we want emitters that can readily respond to an external electromagnetic field. And we want the energy levels of that emitter to be discrete so that we can clearly define the different energy levels. We don't want a continuum, because a continuum means we can't really tune which energy transition we're looking at. And we want the energy levels not only to be discrete but well defined. And similarly, we want that for the box states, for the photon states, for the modes. We want the photon states to be discrete and well defined. We want to be able to pick the photon energies, we want to be able to identify the electronic transitions, and we want to be able to match them. And then an important thing also is, here's the box. These interactions between the emitter and the electromagnetic field are taking place. Photons are being generated. We want time for the photons that are generated to rattle around in the box and to perhaps interact again with the emitter. So we want boxes with low optical loss. And the other way we describe low optical loss in our parlance is high Q. So we want these cavities or boxes with high Q. So before I go and tell you how we implement it, let me look a little bit more at what we've just been talking about. The requirements on the box, the requirements on the emitter, and the idea of coupling. So here's our symbol for the emitter, an exciton. Here's our symbol for just the photon states. And this distance shows that they're not coupled. So you have the emitter, gives out a photon. There's no interaction, no particular interaction between no controlled environment. So, and in this case, for example, let's take, and this applies to a particular material system that I'm going to describe further later on. This emitter has a typical lifetime, a lifetime for decay, and let's say, which is reasonable, that that lifetime is on the order of a nanosecond. So that is the emitter in its sort of unboxed environment. It has a spontaneous emission frequency, it jumps up, emits, and the average lifetime is about a nanosecond. Now, let's put it in the box and see what we might expect. So what I've shown here, indicated here, is that we've boxed the emitter, boxed the exciton, and I've brought the emitter and the photon together a little bit more closely. Now the emitter is in the box. So it is subject to the density of states of photons in the box. It is interacting with the modes, the electromagnetic field in the box. So that has some influence, this back and forth, emit and then re-excite, emit, re-excite. There is now an influence of the environment on the optical performance of this emitter. But the interaction is what I'll call weak. And weak is in comparison to what I'll show you next. But in this case, for example, if we were to measure, if we were to make some measure of how that emitter changes, what might we see? Well, there's some effect of the cavity. And for example, the cavity shortens the spontaneous emission lifetime. The typical lifetime tau x, which was 1 nanosecond without the box, now is reduced by an order of magnitude or so, so 100 picoseconds. And this is something called the Purcell effect. Purcell made this prediction for atomic systems in 1946 that the optical environment could very well change the spontaneous emission lifetime. In his case, he was talking about atoms. And the other consequence of this is we change the spontaneous emission lifetime, we get a brighter output, and that also implies something about the efficiency of the optical process, and I'll show you that a little bit later. So that's weak interaction. Let's go to the next step of the involvement of the emitter with the box. And what I'm showing you here is now we have an emitter in a cavity. It emits a photon, and the photon, the lifetime of the photon and the Q of the cavity is such that the photon can be reabsorbed by the emitter and can perhaps be reabsorbed several times before it actually finally escapes the cavity and we read it out. Now, in that case, the emitter and the box, or the photon modes, are what we call strongly coupled. They're so strongly coupled that we no longer are able to describe, here's the emitter, here's its wave function. Here are the modes of the box, and this is their characteristic description. And they're separate. Now they're strongly coupled, because a perturbation to one is a perturbation to the entire system. So that's the sense of strong strong quantum dot cavity coupling. And a representation here is that we indeed have a new, instead of just exciton and photon modes, we now have a single wave function, a coupled wave function. And there are two, we have two ground states to begin with, or two basis states to begin with. We have two mixed exciton-photon eigenstates, or polaritons. And that's just indicated schematically here. And if we were to look, there are many manifestations of this strong coupling, but we reduce the photon lifetime even further to 10 picoseconds. And what we've achieved here is truly a new quantum state, where we have a coupled photon exciton wave function. And then we can begin thinking, I alluded to the fact that maybe this is going to be a basis for understanding quantum information processing. And here is one avenue to understanding quantum information processing. So this is what we're going to be looking for. And I bring this up because, again, in defining how we're going to realize our system, I think it's important for us to know the degrees of interactions that are possible and what we're going to look for. So, the emitter. We could work with atoms, and as I said, the early work was all done in gas phase with dropping single atoms through atom traps, subject to the influence of a cavity. It's a difficult experimental problem from a number of views, and it has been done already. And for many of the applications we're looking for, it would be nice to work with a system that was in solid state, like a piece of semiconductor, which we use for so many other applications. So what we're going to use for an emitter is not a single atom. It's in fact a collection of atoms. But the important thing is that, at least at the outset, this collection of atoms has some of the optical properties that we're looking for. It has high optical efficiency. It gives discrete, well-defined optical transitions. And so just to show you, here is an electron micrograph of a quantum dot. And you see this lattice work. It shows you the individual atoms. This happens to be cadmium selenide. And this quantum dot was chemically synthesized in the lab of Paul Avizatos. So quantum dot, some of you may know this already. In case there's anyone who is not familiar with these concepts, we're talking here about using as a basis single crystal semiconductors. And we're using a volume of that single crystal semiconductor with that's small enough so that we can pick out the discrete energy levels. That is, the difference in energy levels is greater than the thermal energy at particular temperature of measurement. And that means, depending on the material and depending on the properties, that the diameters of these quantum dots range from maybe 20 to a few hundred angstroms. And for a semiconductor, this is what the band diagram looks like. A conduction band that has discrete levels, a valence band that has discrete levels. You make an excitation, you form an electron-hole pair, and this is, again, my shorthand earlier, that's an exciton because they're loosely associated with each other. So this is an excited state. You take an electron from the valence band and now it's in the conduction band. And they're loosely associated, and actually that's good for many purposes. And then we wait until that excited electron returns, makes a de-excitation to the valence band and emits a photon. So this is going to be the basis of our optical emitter. But the optical emitters of the quantum dots we're going to use are not those chemically synthesized quantum dots. We're actually going to make sandwiches of material, and the quantum dots are going to be embedded in those sandwiches. And the way we're going to do this, and a lot of work at USC has gone on in making quantum dots of this kind. This shows you an atomic force micrograph of indium arsenide quantum dots. Professor Madhukar here at USC has done a lot of work in this particular area, and sure many of the faculty researchers here have used these structures. The idea is to use a two-dimensional growth technique, molecular beam epitaxy, with materials that are intrinsically not lattice matched, to force one material to adopt the other as its template, to force it at the cost of building strain into the material, and letting that strain be released in a controlled way. And the end result is this three-dimensional structure from a two-dimensional growth technique. So this is how we form our quantum dots. I'm going to show you their optical spectra in a minute. Typically, our quantum dots are 30 nanometers in diameter. And what you can see here, roughly from this AFM, is that we have a variation, sort of randomness in the location of the quantum dots. You can imagine that if we had our choice of placing quantum dots on the substrate, we probably wouldn't choose to place it exactly like this. It's just like you had a bunch of quantum dots in your hand and you threw it on the floor. And wherever they fell, that's where they fall. And you can see there's a variation in size of the quantum dots as well. In particular, in our case, there's about 10% variation in size. And the density of quantum dots we have is about 10 quantum dots per square micron. So that's our starting platform. Those are our emitters. What do they look like when we excite them and let them de-excite? This, by the way, is a band diagram. There's something called a wetting layer, and this is the confined region of the quantum dots. And if you look at the luminescence spectrum, there are a bunch of things, without going into too much detail. You can, if you look at these energy diagrams, you can successively excite and see the luminescence from an S shell and P shell and higher. So in that sense, it is very much like an atom. We have different levels, we have different quantum levels. We successively excite the electronic transitions to higher and higher energy quantum levels, and we see those transitions. Now, this spectrum is a spectrum that is representative of, let's say, an ensemble of quantum dots. Maybe we're averaging over an area, this is 1 micron by 1 micron. The spectrum I show you here may be an average over an area of 100 microns by 100 microns. And because there's a variation in size of the quantum dots, you see very broad peaks. So you see very broad transitions which give you the average variation of quantum dots. That's actually not what we want, but actually when we focus on individual quantum dots, we see that we get what we need. So here is a spectrum of an individual single quantum dot. This is the photoluminescence measurement taken at 4 degrees Kelvin. And what you notice is that you can see very discrete transitions. The widths of those transitions are narrow. They're on the order of a few microelectron volts in width. These widths are about 1,000 times broader. This is the kind of spectrum we want. And where I've labeled it X plus, X0, XX, X minus, X stands for exciton. This is a neutral exciton, an electron-hole pair. This is a positively charged exciton. This is a bi-exciton, 2 electrons and 2 holes, and this is a negatively charged exciton. So they all have characteristic energies, and you can see we can clearly distinguish between the various flavors of excitons. So that was our emitter, and now let's talk about our box. And it turns out our box, again, what we wanted to remind you is we want a box that was pretty small in volume and very lossless. So high Q, very small volume, that could encompass our emitters. And the kinds of boxes that we're going to work with, again, we're working in the solid state. These are 2 scanning electron micrographs of gallium arsenide with holes punched into them. These are called photonic crystals, photonic crystal cavities. And if you're not familiar with the concept of photonic crystals, I'll tell you why these are ideal. These form good boxes for the emitters we're going to use. You can tell that, and I haven't told you the whole, these are actually membrane structures. So the volume, the dimension in the Z direction is about 100 nanometers. But you can see here's a 500 nanometer bar. So the volume, we're going to have actually, the box is defined by this solid piece within this fabric of holes. You can see that the volume of these resonators are going to be fairly small. And I'll show you what the quality factor looks like. Now, to backstep a bit, maybe all of you are familiar with the idea of photonic crystals. The name photonic crystals borrows from the idea of regular crystals. A regular crystal, here's an electron in a regular crystal where the electron travels through a periodic variation in potential. And that periodic variation in potential is set by the regular lattice environment that is set by the atoms in the crystal. And you probably all know that as a result of the periodic variation in potential for the electron, it gives rise, if I plot momentum versus energy, it gives rise to energy bands. And depending on the material, you have a band gap. If it's a metal, a semi-metal, there's one kind of band gap. A semiconductor has a band gap on the order of electron volts to a few electron volts, and then insulators have higher band gaps still. So, but the important thing is this regular periodic variation of the potential for the electron produces this band structure and this band gap. So what's the analogy for a photon? This is an electron traveling through a periodic variation. For a photon, what would constitute a periodic variation for the photon? Well, one thing you can use is you send a photon through a terrain of varying index of refraction. So it might look something like this. Sorry for the photon lost its end. So photon travels through a structure where there's a periodic variation or modulation of index of refraction, and the same thing happens. That is, it gives rise to a band structure, but it's a band structure that defines the allowed states of photons rather than electrons. And similarly, given the dimensions of the holes and the symmetry, you can form a band gap. So bands for photons and band gaps. That band gap says that any photon that has this particular frequency cannot travel. There's no allowed energy state for that photon, cannot travel through the material. As it may seem counterintuitive, it may challenge your feelings about physics, but in fact, that does work out. But we're not quite there yet. Those are photonic crystal structures. Why are we using photonic crystal structures to define our box? Well, because our actual photonic crystal structures are not perfectly periodic structures. If you look at here's an example of a photonic crystal cavity or resonator. We have neglected to etch out a hole right here. And in that sense, that deviation from periodicity, it's like a defect. So think about, from the electronic point of view, what would a defect do for an electron? If you had a defect in an electronic crystal, what is one way you would know? Well, one way you would know is if you have a band gap, and you have no allowed energy states for an electronic, for an electron or electronic energy state, but then you introduce a defect, that defect is often represented as the introduction of an allowed energy state within the forbidden gap. So what happens to electrons often? They're in the conduction band, they see this lower energy state, plop, they take that lower energy state and they may be trapped. We say that they're trapped or they're localized. They're localized, and depending on the structure and the temperature and a variety of other things, that electron just sits here. It's happily in the conduction bands traveling along, plop, falls on the defect, the localized state, stays there for some lifetime, and then may be excited back up to the conduction band and happily travel along. So the important concept here is that the electron is localized at the defect. And in the same way, if we use by analogy, the defect in the photonic crystal creates photonic states within the forbidden gap. Those photonic states then can localize light within the resonator and produce a strong optical confinement of the photon within this defect. Now, what does it look like in terms of, I'm saying that this is a way, obviously, of making a cavity that's very small in volume. And again, looking here, this is 500 nanometers, this line, and so we have holes that are on the order of 100 nanometers or so, separated by about 100, 120 nanometers. So the volume of this cavity is very small. What does the mode actually look like? And here is a simulation looking top down and looking, again, I'll show you, but our photonic crystal structures are membranes. So this is a piece of semiconductor that's freely suspended, and where you see the brightest, the yellow, is the highest intensity electromagnetic field. So the yellow shows the concentration of highest field strength, and then it tapers off to the red. And you can see here this is the characteristic mode pattern of this particular photonic crystal defect. And this is what the mode pattern looks like if you take a slice of the membrane. And actually, this provides us, although we won't do the detailed calculation, looking at this gives us a good idea of actually what the Q will be, theoretically. That is, will there be a lot of optical loss, or will this be a high Q material? And one way we can tell is how much the evanescent field tapers out into the environment. If most of that evanescent field is concentrated in the semiconductor, then basically those modes and those photons stay in the semiconductor. Now, there are other things that can happen. You can damage the material. There are other sources of loss when you actually fabricate it. But one way to tell at first in designing a structure is what does the evanescent field look like? This is a linear scale. I just wanted to show you that if you plot it on a logarithmic scale, actually you can see quite a bit of the field is coupling in plane and out of plane. But in this case, the Q, the quality factor, the factor that tells us how much optical loss there is, so the higher the Q, the less the loss, can be measured if we look at a spectrum by the wavelength over delta lambda. And you'll see some examples of that in a minute. So how do we fabricate it? That is the idea. That's why we're using these resonators. How do we fabricate it? We start out with a sandwich of material grown by MBE, gallium arsenide, aluminum gallium arsenide, and then our sandwich of quantum dots. We use electron beam lithography to define the features that we need. We use that as a mask, and then we transfer through a dry etch into the gallium arsenide material through the quantum dot material and partway into the aluminum gallium arsenide. And then to create our membrane, we use a selective wet etch. And the result is something that looks like this. So that's how we fabricate these membrane structures. That's how we make our boxes. What might it look like if we measure the photoluminescence? Well, again, here is, we usually use micro photoluminescence, And our exciting source, sorry for the loss of the wording, it's the exciting source is a laser that operates at 780 nanometers, and this is all low temperature. This is done at 4 Kelvin. We focus the laser line in through a microscope objective to a structure that may look like this. We call this an L3 cavity because it's linear. We've taken one line out and we've taken essentially 3 dots out. So that's the terminology. And if we measure, now remember, you can't see it, but embedded within this cavity are quantum dots on the order of 5 to 50 quantum dots per square micron. So in this particular case, we actually have a high density of quantum dots. We shine light, we look at the response of this cavity, and we see an emission peak that looks like this. Remember, Q is lambda over delta lambda, and this particular Q is pretty high. It's 20,000. Okay, so to recap, we've taken quantum dots, we've grown them by MBE, they're sort of all over the place, there's a 10% variation in size. So the placement is random. We cut out this photonic crystal structure, we've made the box, we shine light, looks pretty good. I think it's telling us that we have high quality quantum dot optical emitters, high Q cavities. Remember what I said at the very beginning about something that's important, spatial resonance and spectral resonance. We've done nothing here to ensure that there's either. This is a completely non-resonant case. We haven't changed the positions or tried to adjust the positions of the quantum dots. We haven't done any matching of frequency. And yet, and this is an example of what happens, this is the power of thinking in the box for a weak coupling case. And yet, for this structure, and I'm showing this again, this is the structure in gallium arsenide, this is the mode profile. This is the quantum dot, these are the quantum dots that we can't see that are embedded, and they're from, we do a calibration. This is an AFM, we grow the quantum dots, we take it out, we measure the AFM, but the final structure, we can't see this. In the final structure, we've grown other layers over it. But we know that there are about 1 to 3 quantum dots within this region. There are about 1 to 3 quantum dots. These quantum dots, because there's a variation in size, we expect them to emit at frequencies that are spread out over between 50 and 100 nanometers. So I'm just reinforcing the point that we don't know where the quantum dots are, so we don't know anything about spatial resonance. The variation of the frequencies we know is pretty broad. There's about 1% probability of making both spatial and spectral resonance. 1% probability. We've done nothing to achieve that control that I want, and yet, if we look at these samples, out of 20, 25 samples that we made and measured, 80% showed lasing at low thresholds. So here's an example of the line width, and they varied indeed. I said that the emission line widths vary over between 50 and 100 nanometers. We have a set of lasers where there's single mode lasing here, 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 and this graph is indicative of the kind of thresholds we get, where this is just, if we measure the spontaneous emission background, this is where we see lasing. So as we increase the pump power of the laser, we see the intensity go up dramatically. And here we extrapolate a threshold of 124 nanowatts. This is just a polarization measurement that verifies that indeed we're looking at lasing. So all of these lasers, none of them were controlled so we get that spatial and spectral resonance. And yet 80% of all these samples actually show lasing with ultra low thresholds. And the question that I'm going to leave you with, and I'm going to pick up later, and I'll tell you we don't have the full answer. We only have more puzzles. How can 1 to 3 off-resonant quantum dots in a photonic crystal cavity be so efficient? How come that all 80% of these samples lays with such low threshold. I haven't done that strategic match, and yet something happens, seems to be tuning those quantum dots and the cavity into resonance. So let me move from that for a moment and go to the next topic, which is, okay, that was completely non-resonant. Now we would like to control the box and the emitter a little bit better. So what we're going to do, and this tells you the situation. First of all, there's no resonance in frequency. This is the mode. This is the emission from the mode of the box, and these are the exciton transitions. So you can see that they're emitting at a variety of different wavelengths. You want them to be coincident, but here the mode is at 955 nanometers and this exciton is at 940 nanometers. So there's spectral detuning. They're not matched. And the other thing is, if I superimpose this picture of photonic crystal over the AFM of quantum dots, you can see, if you remember, the maximum of the mode is right here, and there's no quantum dot right there. So there's a spatial misalignment. So this is the problem. And this is what was true for the lasers I just showed you. How do we proceed to solve that problem? So first, let me just tell you a couple of quick ways that we do spectral tuning to compensate for the detuning. And spectral tuning is we take the box, and like an organ pipe, I used the analogy of an organ pipe before. An organ pipe is a cavity or a resonator. And depending on the length of the organ pipe, the cross-sectional area, you get a different acoustic tone. So the geometry, the size of the resonator, determines the response of that resonator. So one thing we can do is just see if we can fine-tune the geometry of the resonator even after we fabricated it. Here's an example. Okay, so here's the mode. Here are the excitons. Again, they're way off. They're way off in frequency. They're not matched. Here's a side view of the photonic crystal slab. And one way to tune it is to finely chip away at the resonator. Change its geometry so that you can change the response of the mode. How do we do this? We actually use something we call digital etching. We use an etch that forms an ultra-thin oxide, native oxide layer, and then we remove that oxide in acid. And does this work? Well, here's an example of what we were able to achieve, starting 3 times. That is 3 times we oxidized and removed, oxidized and removed. You see the mode is moving over closer to the emitter transitions. 5 times moving more closely, almost overlapping the charged exciton and moving closer still. So this is one way that we can fine-tune the response of the cavity. And just to tell you, again, this is another example of weak coupling, but the power of weak coupling. What we did is, here's another example. Here's where the mode started. Here are the exciton transitions. And notice that as we tune the mode to overlap in frequency with the emitter transitions, something happens. We don't only get that resonance, but all of a sudden we get a huge increase in intensity. And that's indicative of the fact that once you get that match in frequency, there is that really efficient exchange of energy from the emitter to the resonator and possibly back again. So from here to here, you have a huge increase in intensity. You have a huge increase in intensity that's emitted outwards, and that's indicative of both the increase in efficiency, which we saw with the low threshold lasers, and this is the potential for a high brightness source. And so here's another example of this. The red dots are off resonance, off frequency resonance, so here. The black dots correspond to the on resonant condition, and then we increase the pump power. You see that part of this, the blue, is just because of the symmetry of the mode. We expect higher extraction efficiency, but there's a part of that increased intensity that we get between off resonance and on resonance that is produces net 700 times intensity enhancement. And part of that is this, I talked about a Purcell factor, a change in spontaneous emission lifetime. This Purcell effect says that the cavity really is influencing the emission dynamics of the emitter. And this is just to tell you that for a series of different starting wavelengths, we can do this digital etch 20, 40, 50 times and tune the mode, the frequency of the mode from 980 all the way to 880 practically. That's a huge tuning range. And the important thing is, as we go through those etches, you see the quality factor, the goodness of the resonator basically doesn't change at all until you do maybe 15 of these digital etches. I'm going to skip over the next one. We also managed to tune it by writing AFM oxides onto the cavity. That's another way of tuning one mode with respect to another. But what I want to get to the final part, something that we worked for a long time, which is to go beyond weak coupling and to also look at this. We just looked at how we can tune what the mode into the emitter, so to achieve frequency resonance. Now, what do we do about this spatial misalignment? And what happens when we get both frequency resonance and spatial overlap? So in this case, what we did is, without going into too many details, here's the quantum dot. And we grow a low density of quantum dots. So here's in cross section. And what we've done is change the quantum dot growth a little bit. So what we do is leave a little bit of a bump on the top. So this is 60 nanometers, 600 angstroms away. We can work with that. This is the sufficient cladding for the quantum dot. And yet we grow under conditions where we leave a slight signature of the fact that there's a quantum dot buried underneath there. That is the quantum dot we want to align to. So we first put a metal marker. We look for this little bump, and we use AFM mapping to point out where that is. And using this information and the distance of the bump from the metal marker, we just align and write our photonic crystal around it. So we place that quantum dot at exactly the right place at the maximum of the mode. And so here's another view of the AFN, showing that there's only a single dot in the cavity. This surface bump, by the way, you might not know to ask, or you might be wondering, but this surface bump, this sort of little roughness in the surface of the structure, does not affect the cavity Q. And if we look to see, here is again, the simulation tells you where the max and the mode is. We look afterwards to see where the bump is, and in fact, that indicates that the quantum dots should be right here at the maximum of the mode. So, okay, what do we do now? Now that we have this. And the short answer is that when we can achieve both the spatial resonance and the resonance and frequency, and basically what I'm showing here is tuning the frequency. So we've just gone through the whole procedure of actively aligning the quantum dot and writing the photonic crystal around it. So the photonic crystal, where the maximum of the mode of the photonic crystal is, the dot will be right there. So the dot will be most sensitive to the maximum of the electromagnetic field. And now we tune the mode. I showed you before tuning of the mode, and here is the mode. Here is the exciton, and we can actually, we have other ways to tune the position of the mode, do fine tuning. In this case, we do a monolayer condensation. That changes the geometry, it changes the net index of the resonator, and therefore changes the mode. And what you see here is as we tune as we begin to tune, and this is detuning, so detuning, we begin with 0, tune one into another. You see, let me show you this here. So we start out, the quantum dot is in the resonator. Now we start shifting the position of the mode with respect to the emission frequency of the quantum dot. Now here's the critical thing. If in fact the photon modes and the excitons are really one wave function, if they are strongly coupled, as we tune one to another, so let me say this is the exciton and here's the mode, and I'm walking the mode across until it should come into frequency resonance with the exciton, and then I keep walking it beyond. If the exciton and photon had no relationship to each other, there was no particular quantum mechanical constraint on them, then I should be able to see the two of them at exactly the same energy. If they are part of a coupled wave function, you've done this in quantum mechanics, as I bring them closer and closer together, I will not have this exact overlap. I will not have them cross. I will actually have a splitting when I bring them really close together again, because it becomes two components. It's a wave function with a split in energy, and I get something that's called anti-crossing. And that's exactly what I see. These are the experimental points for the mode and for the exciton. So I start out, here is the mode in blue, here's the exciton. I start tuning here. As I get down and tune the mode closer to the exciton, I reach the point of minimum energy difference, but I can never cross. Those two lines never cross because they are strongly coupled, two different manifestations of a single wave function with a slight energy difference. And then as I continue to continue to tune the mode, I again see now here this peak belongs to the exciton, and that peak belongs to the photon. So this is what happens. This is actually what we've reached the limit of strong coupling. We've engineered a wave function where we've strongly entangled the electronic states of the emitter with the photon states of the mode. I'm just going to have a few more slides to actually go. So I could have stopped there. This is the result of many years of work. This is the goal we've been looking for. But whenever you think that you've reached the goal that you want, if you've done a really good job and your experimental data are really good, what you should find out is that you actually have more questions and you don't know all that you think you know. So if I look again here, here's the condition of anti-crossing that I'm very happy about. This suggests that here I should have basically two peaks, one due to a mode, one due to the exciton, and even here where I bring them close, when I have a single strongly coupled wave function, I still have two different states of a combined exciton and photon. But if I actually look closely at my spectral data, what I see is three peaks. I see over and over again something that looks like this. And the question is, why do I see three peaks? I was expecting two peaks. Where did the third peak come from? And actually, in order to find the answer to that, we actually looked at a paper written in 1996 where the atomic physicists help us out, where they did a similar experiment. They looked at this anti-crossing. They did basically the cavity QED experiment that I described to you, but they did it with single atoms in an atom cavity. And they noticed this third peak as well. And fortunately, they gave us the insight to say what they found is that there were fluctuations as they were measuring their atom coming through their cavity and interacting with the photon modes. They noticed that often there'd be another atom passing through their trap at the same time. That other atom coming through the trap at a strategic time actually puts the entire emitter off resonant. with the cavity. And so what you see is these are the two modes, these two peaks. Those are the coupled modes. This is actually the single mode, the single uncoupled mode. And that's because something happens in a very fast time frame. It's a fluctuation that brings the whole system out of resonance. So this third peak is actually the remnant. It's the mode. These are the peaks that have to do with the coupled photon-exciton wave functions. And the third peak is what happens when you upset that delicate resonance of frequency resonance and spatial resonance. So what can happen in the solid state? Those of you who have studied this will understand it, and for those of you who haven't studied semiconductors and excitons, think about this a little bit. Here's the situation. Here's your quantum well. Here is an exciton. Here is an electron and a hole. And this particular transition gives an emission, an exciton transition that is resonant in frequency with the cavity. So at this stage, if there's a frequency resonance and spatial resonance, you get exactly these two peaks. If there's not a resonance, what if all of a sudden you get a charge from a local defect, and that charge happens to be electron? That charge from a local defect comes in, fills the well. So instead of having this neutral exciton that was in resonance, you have this charged exciton, and now you're off resonance. Your emitter is no longer in frequency resonance with your resonator. You don't see these coupled wave functions, you just see the cavity mode. And so because we're time averaging, we sometimes see the strong coupling, and sometimes we see the mode. And why that's really important is it is giving us really sensitive insights to what's happening in the neighborhood of this quantum dot. It's a noisy, messy environment where charges can hop around from site to site. And the fact that we sometimes see this resonance, sometimes doesn't, tells us exactly what's happening in that neighborhood. And let me skip over this and actually just leave you with one piece of data and then summarize, which is, if you remember, you talk about, these are the exciton transitions. And these are the exciton transitions before I make a cavity around the quantum dot. After I make a cavity around the quantum dot and I measure the same spectrum, the same emitter in a box, I see the cavity. This is the mode, but the mode is at 963 nanometers, and the original excitons were at 954 nanometers. Now think about this. Why should this be puzzling? It should be puzzling because this is where the excitons are. These excitons are obviously interacting with this cavity mode, but this cavity mode is at 963 nanometers. These excitons are at 954 nanometers. That says the excitons and the cavity were not in frequency resonance. They were not in frequency resonance, and yet all of the energy from the excitons are transferred to the mode. This is a little bit like the situation I showed you for our ultra-low threshold laser, which was a different situation because we had a lot of quantum dots. They weren't aligned. It was a lot messier. We had several quantum dots. We only have a single quantum dot here. So this is one of the many questions, actually, that have been posed to us since we've gained the insight of actually making this beautiful system where we have a single quantum dot strategically placed within the cavity, and ideally where we can tune the frequency resonance of the emitter and the box. So to conclude, what I've tried to indicate to you is that sometimes thinking inside the box is a good thing and can offer all kinds of creative possibilities. Our box in this particular case is a photonic crystal cavity, and the emitter that we're using are quantum dots. Among the scientific opportunities and creative applications are coupling interactions that produce very low threshold lasers. And then finally being able to achieve new quantum states, coupled quantum states, that we can use as the basis to understand in more detail the detailed time-resolved fluctuations of the semiconductor environment and the electronic traps involved, and maybe even use this as a basis for new ways of quantum information processing with entangled new quantum wave functions. Thanks very much for your attention.
So we have time for some questions.
So it seems like it might be a bit less laborious if you, instead of tuning the cavity, you could tune the dot. So couldn't you, for example, put it in a high voltage or something like that and get some analog of the Stark effect to shift the resonances of the dot?
Actually, there are many. Tuning the frequency response of the dot is not so much the problem. It's positioning the dot that's more the problem.
So you would still have to etch the cavity around the dot, but then get it at exact resonance, it seems like it, rather than easily etching the cavity, you could just adjust the strength of some.
And I think what you're suggesting may be a good way of reversibly tuning, but the issues with applying a field here from the pragmatic point of view is, in order to apply a field, you have to apply metal. You have to have some way of inducing the field. You have to, so think about how you might, this is a narrow membrane, underneath a semiconductor, on top is nothing. It would be a tour de force in fabrication, although it's possible to do it, to actually create metal electrodes that are lossless and to create a sufficiently high field to tune it. And so people have done this tuning of quantum dots and the quantum dot position, but most of the time that means putting metal directly on the surface and to have the highest field in closest conjunction to the quantum dot. That destroys the Q of the photonic crystal. So from the pragmatic point of view, from the fabrication point of view, it's much more difficult to do. But you do bring up the good point of looking at alternative techniques to reversibly tune the two.
You can't just stick the whole thing in plates that are pretty far away. I mean, is that just not to go as far as you?
No, I mean, you have a piece of semiconductor. I mean, think about it. You have a plate, very high field. If you apply a field that's high enough, the breakdown, and you have to apply a uniform field. The other thing is that I should say that some of the tuning methods, even though I talked about particular techniques that we use to tune the modes, we use monolayer condensation, and that is reversible. So there are techniques that are not so difficult to work with. The temperature is stable, and you can temperature tune it, but the temperature is stable, and it happens at any temperature. And I just want to, in terms of the wetting layer, can they communicate through the wetting layer? Yes. Do you expect to see a transition because of wetting? This is the wetting layer transition. It is, so this is plotted in electron volts of energy rather than nanometers of wavelength. This is 0.2 electron volts of energy. So it's not, can you communicate through the wetting layer? It is a possibility, but the question is how. So what I'm suggesting in terms of destroying the resonance is just a single charge hopping on to the quantum dot. A single charge. You don't even need a wetting layer as a contact. It can be a single charge that's trapped in a defect and then just hops into the quantum dot.
After
There's one quantum dot in the resonator. So the last data I showed, there's a single quantum dot. The other quantum dots are very far away. They're not even in the resonator. So the wetting layer is everywhere, but so here is a wetting layer. You're measuring something that it's a steady state, so you do the excitation, you give everything a chance to decay. It may be that the charge trap is in the wetting layer, but it could be anywhere. You don't need the wetting layer to do that kind of communication and to change the position. Yeah.
Okay, we get more control over the quantum dot position. Is there any way to get like a highly ordered array of quantum dots?
You ask a good question, which is to suggest that instead of having something like this, if you had a highly ordered array of quantum dots, maybe you could map directly. So I'll say the following. There's been a lot of work, actually before we started our work, there was a lot of work in doing ordering of quantum dots. People have used strain engineering, people have etched dimples, people have ordered the substrate in a variety of ways. There are a couple of problems with that. One is that many of the techniques involve processing the substrate in some way. When you process the substrate, if you change the morphology, if you change the texture, the surface, you can profoundly change the Qs, and we know that from one of the techniques that we use. You can profoundly degrade the Qs. The second is that it happens that if you do any pre-processing to the substrate and then grow the quantum dots, almost inevitably there is some defect. You carry some defect or some memory of that processing into the optical properties of the quantum dots. The last thing is, suppose you were able to grow this in an ordered way. I mean, perhaps you can have a marker way outside here. Even if you were to grow this in an ordered way, and if the top surface, if you continued growth so that the top surface was fairly smooth, you still wouldn't know exactly. You know that it's ordered, but you wouldn't necessarily know where you know it's repetitive and ordered, but you might not know the exact position to co-locate with the maximum of the mode.
It's possible to first build this array, then drop a bunch of dots on top, move them around, probably do where you want them. Tremendous.
So we're exploring that, and I think what you're suggesting is we are looking at that, and I think other groups are looking at that. So, but what you're suggesting is not an epitaxial growth, because once you've treated and processed a substrate, you can't regrow by MBE and have good quality. So the point here is this: can you place a quantum dot on top of the surface, let's say a colloidal quantum dot, so that it feels the influence of the evanescent field and therefore can couple to the field, so that it's close enough that it won't quench, that it couples, and can you position it? And that's a question. So there are a lot of challenges there, but that's another approach to trying.
Certainly could manipulate them wherever you want.
Right.
They could be.
Well, we're running a little late for the reception outside, and so I think what we'll do is cut off the questions at this point, and I'm sure that Dr. Hu will be happy to answer the questions outside. I have been, however, given the responsibility of rewarding you for this excellent talk. Well, first of all, I think we should thank. Those are really a beautiful set of experiments, and it's a tour de force. It has become a tradition in this seminar series to present the speakers with highly valued presence that few in the world possess, and only those who come here and make presentations. And so I've been given the honor of presenting these things to you. And so the first of them is, of course, a pen. You know, got the USC logo on there, and will, I'm sorry, make you the envy of all of your colleagues at UC Santa Barbara.
I'll value this.
The second thing is a mouse pad, which is colorfully covered with the Viterbi School of Engineering logo. But the most important thing, the thing that will set you aside from any other, is a genuine Ming Hsieh T-shirt that commemorates the gift that was presented to our school by one of our alumni. So I present that to you and wear it in good health. Thank you. And a little bag to carry these things.